Hi, how's it going? My name is Carl Dees with the Learning Resources Center here at the University of Colorado, Denver, and today we're just going to go through two questions looking at graphs of periodic motion. So let's get going. We're given some questions here. We're just going to answer them. Here we were given this graph we have to draw. But we were given that for this first question, we were given this graph where the maximum amplitude of this thing is 2 meters, and we can see that down here is the time. Right, these are the seconds down here. So this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds, 8 seconds. Okay. So they asked this first question: at what times are objects moving right with max speed? Well, at times 3 and 7, 3 and 7, we can say here, because the slope at that time, if this graph is being made like this, the slopes at 3 seconds and 7 seconds, right? That's what this is. The slope is up, which means that the box or the whatever they call it, a box, but this doesn't have to be a box on a spring. The object that's oscillating is going to be moving. We're saying that must be the positive x direction, is moving in the positive, but based off the way that we make these graphs. We know that when the slope's positive, we're moving in the positive x direction. So we see that there's a positive slope here. We know we're moving in the positive x direction, so that 3 seconds and 7 seconds, the positive slope means we're moving to the right, with max speed, because right we're considering positive x, and left we're considering negative x in this case. Okay. At what times is the object moving left with max speed, or to the negative x? Well, we know that the left, or negative x, is going to be negative slope. So at 1 second, right, 5 seconds, right, and 9 seconds here, we see the slopes here. Again, this graph is being made like this. So here we're going up, but here we're going down, here we're going down, here we're going down at 9, 5, right, and 1, we know we're going down. So that since the slope's negative, we know we're moving in the negative x direction. So at those times we would be moving left. And again, how do we know? Because there's something here with max speed that I didn't quite explain with the first one. How do we know it's at max speed? Well, we know this is max amplitude. We know when we get to this point, we are at equilibrium. Okay, that's the equilibrium position for this object in simple harmonic motion. And we know at equilibrium, that's max kinetic energy. So every time we get back to this point, this line right here, we know we're back at equilibrium, which we know we're moving at max speed. So then for both these questions, then it's just a matter of looking at the slope at that point, right? At 3 and 7, the slope is positive, so we're moving to the positive x or to the right. At 1, 5, and 9, the slopes are negative at that position, and so we know we're moving to the left with max speed. When is the object instantaneously at rest? Well, here we're assuming that we pulled it, and that's where we let it go, right? So it's not instantaneous at rest, we were holding it at rest. But everywhere after that, anytime we see a max amplitude, we know the object is stopped and is headed back in the opposite direction. Like if it's oscillating, jiggling, right? It's stopped here, it's going to head back this way, stop here, head back this way, right? Everywhere at max amplitude. So when is the object instantaneous at rest? We can say at 2, 4, everywhere you want to look at there's max amplitude, that's when we're instantaneously at rest, except at that at that position where we're holding it, okay? And when is position maximum? It's at the same time that we're instantaneously at rest, but we could also say it's 0. So I didn't put it in here, but at time equals 0, right? We know that we're at max position, but we also know at 2 seconds, 4 seconds, 6 seconds, 8 seconds, everywhere that curves, right? We've hit a max position, okay, or a max amplitude. So that's how we know where those are at on this graph. What is period? Well, we know period is how long it takes to make one full cycle. There's a lot of ways to look at one full cycle here. We can look peak to peak, so we know this is one peak, this is another, right? So that's one full cycle, which is a period. It's also the wavelength, right? But we see if this is 0 and this peak happens at 4 seconds, right? Then we know from peak to peak, that's one period. That's how long it takes to make one period. That's 4 seconds, so we know 4 seconds is the period here, okay? And you could look at it under, if you wanted to start here, right? If you're comfortable looking from here to here, you could have said, okay, from 1 to 5, how many seconds is that? it's the same, right? 1, 2, 3, right? You start here, 1, 2, 3, 4, 5, right? Because this is also, right, one period. Again, period is one full cycle, one full oscillation. Typically, I like to look peak to peak, but you can also look right starting here, and then that would be one full cycle right there. This is not one full cycle here to here, that's just half a cycle. This is one full cycle there, okay? So however you want to look at that, but we know the period's 4 seconds. What's the frequency? Well, if we know the period, we know the frequency, because frequency is just 1 over period, and if period's 4 seconds, right, we know frequency is just equal to 1, this would be 1/4, or if we do the math, it's 0.25 hertz, okay? So the frequency is just 1 over period. If we know the period's 4 seconds, then frequency is 1 over 4, all right? That's what we're saying here. What's the phase difference between 2 seconds and 4 seconds, right? Well, 2 seconds is right here, right? 4 seconds is right here, all right? Well, we know for one full oscillation to get from peak to peak, this full period, right? We know that's 2 pi, right? That's 2 pi. Oops. One full period is 2 pi. All right, we know that. And so what we can see here is that this is peak to peak. What we can see is from 2 seconds to 4 seconds. That's only half a period, right? So only half a period is only, and if 2 pi is equal to 360 degrees, right? Then from here to here, that's only half a period. Half a period is going to be 180 degrees, right? Or pi. All right, so we know that a full period is equal to 360 or 2 pi, but half a period, right? And we can tell it's half a period because it's just going from one peak to the next peak. If it was going from peak to peak, like we said here, then that would be different. But if it's going from a trough to a peak, that's going to be half of a wavelength, which is going to be 180 degrees difference, or pi. Okay. Again, if they ask what's the phase difference between these 2 points, between 1 second and 4 seconds, it would be 2 pi. Okay, because that's one full oscillation. Okay, since this is just a half oscillation, it's just pi. Okay, the phase difference is just pi. All right, now for over here, we are told that we have an equation for simple harmonic motion that's given like this, where this is the second question. Sorry about that. So that's all for this question. Moving on to the next question here, again, another simple harmonic motion question with the graph, where we're given this equation. We're saying, okay, we're given this equation for simple harmonic motion where x of t, right, or x as a function of t is equal to a sine, and then here, right, we see omega t. Omega, right, you're used to seeing this as omega t. I know we write this equation as x of t is equal to a sine omega t. That's how you've seen it. But we know, right, omega, right, is equal to 2 pi over t, because we know period is equal to 2 pi over omega, so we swap these and we know that. So omega can be written as 2 pi over t, which is what you see here. So this is still omega, it's just written different, all right? So they asked us some questions here. What is the value of x when t is 0? Well, we can make t 0. If we make t 0, that's going to make all of this term 0. T 0 makes all this 0, which means a sine theta times 0 is 0, means x is going to be equal to 0 at that point. Again, when they say when t is 0, you're literally putting that number in place of t, because this is a function of t, so we just replace t with whatever they told us. Here they said t is 0, so we replace t with 0. All that's going to be multiplied by 0, which means anything multiplied by 0 is 0, which makes this whole thing, this gets multiplied by 0, which turns all this to 0, and this is going to multiply by this, which is going to be 0 already, so that makes it 0. So x equals 0, t equals 0. When t equals 0, x is going to be equal 0. So right there is what they're telling us, right? When x is equal 0, when t is 0, x is 0, all right? And I'll come back to these n equals 1s here and zeros in a second. Now they ask, what is the value of x when t equals 1 t over half, or half a period? So what you want to do is, again, replace t with half a period, which is what I did here. Now I didn't write the whole equation out, I'm just looking at the function. So 2 pi t is this part, but then I replace t with t over 2, because that's what they're asking us to do. What is the value of x when t is t over 2? So I replace t with t over 2. Again, I could have written all that, but I'm just looking at the function right now, all right? So when I do that, I see the t's are going to cancel and the 2's are going to cancel, right? So everything inside this parentheses is going to disappear except the pi, right? The 2 is going to go away because when they said t over 2, this t on the bottom is going to cancel, right? And this t is going to cancel with the original t that was in there, leaving just that pi. All that's going to be left is that pi. So when we put it into the equation and write the equation as a sine pi, we know sine pi is 0. So again, that makes this 0. A times, if sine pi is 0, that means this is 0. Amplitude times 0 is going to be 0, so x is going to be equal to 0 again. Okay, and we can see that we're kind of setting up a pattern here. So when t equals 1 or half a period, right, we're back at x equals 0. And that should be true. This is trying to show you something about simple harmonic motion. All right, and that's true. And this will be true for all objects in simple harmonic motion. And then it goes on to ask us at what 2 other times does x have the same value as when t equals 0? Well, like I said, we want to kind of look at something here. Okay, and we can kind of see by this pattern that we're forming. Now we started with this first one, right, where we said this was the first dot we got, right, and then the second one we got, right, when they asked when t is equal to half a period, right, was this one. So we see that, maybe there's, and we know this is going to be simple harmonic motion, that maybe there's going to be kind of a pattern here, and there is. And what we see is that time is actually just going to function in terms of an integer, right? So that t half, right? We see that every half of a wavelength, x is going to be equal to 0. So when they're asking us, what 2 other times does x have the same values when t equals 0? When t equals 0, x equals 0. So they're asking us, at what 2 other times will x equal 0? Well, if it's based off this periodic motion, we can literally just take that t and or that half a period, since that x is 0 every half of a period, and multiply it by a functioning integer. So let me show you what that means. So for the first one, if we were to use this at time functioning as an integer of half a period, when n equals 0, right, we're going to multiply all this by 0, so t is going to equal 0, and then when we put it in here, x is going to be equal 0 for the reasons that we already said. Now what about the next one? What about when n equals 1? Because when we say that time's going to function in terms of an integer, what we mean is that we can just write n in terms of 1, 2, 3, 4, 5, no numbers in between, but 1, 2, 3, 4, 5, okay? So the next integer, if this is n equals 0, the next integer, n equals 1, right, should give us 1/2 t. So when we put n in there, right, n equals 1, which means time is going to be equal to t over 2, right? And that's what we said. What is the value of x when time is equal to t over 2? Well, when n equals 1, time is equal to t over 2, we know again that x is equal to 0 at that point. So it's working. This idea of having time function as an integer of half a period, because we know every half of a period we're back where x equals 0 is working. So what we do is we just continue with that. So the next one, the other 2 times, right, we should just be able to make n equal to 3 and for one of the times, and then for the other time, because it's asking for 2 times, right? So for the next time, we've already done n equals 1, or n equals 0 and n equals 1. I'm so sorry. For the next ones, right, we can do n equals 2, and n equals 3, and n equals 4. I think I skipped n equals 2, but let's do that here. Let me write it down real quick. So for n equals 2, right, if we were to do time as an integer of 2, we'd put 2 in there, right, and we keep that t over 2. It's just the n that's turning into an integer. So this is when n equals 2, right here, okay? I just noticed I didn't do it. I did n equals 0, n equals 1, and I skipped to n equals 3. I don't know why, but this is n equals 2, okay? So if n equals 2, I want to replace that n with 2, which is what I did here. These 2's are going to cancel, which means time, right, should be equal to a whole period. And at that point, when we've reached a whole period, we're saying that x should be equal to 0 then. So when time's equal to t, which is true. So if we put t in here, right, we can see that. If we were to put t in there, right, in the 2 pi over t, and we replace time with the t we just got using this integer idea, right? If we put it in there, time is just going to be equal to t here, which I'll do in blue. Those times are going to cancel, right? And now we're just left with 2 pi. Well, that 2 pi is going to go in this equation, right? So then we're going to have x over t, right, is equal to a sine 2 pi. Well, right? And so we can see that over and over, right, as this, right, where t equals 0, that's where x is going to equal 0 again. We can see that this number, right, when we use that, that is also going to get us, right, that's where sine is going to also equal 0, right, when it's sine 2 pi, that's going to be 0, which means x is going to be equal to 0 there. So we can see that when n equals 2, we're using that integer in terms of time, we get x equals 0 again. And the same thing happens when n equals 3, okay? So again, using time, and I hope this isn't complicated. I'm not trying to make it complicated. You just understand what I'm doing here. Because this is simple harmonic motion or periodic motion, right? We can see that every half of a wavelength, x is going to be equal to 0. So if that's true, right, we can take every half of a wavelength, or every half of a period, I said half of a wavelength, but it's every half of a period also. You can write it either way. But every half of a wavelength, we see that x is going to be equal. So when time is equal to half, some integer of half of a wavelength, we're always going to be where x equals 0. That's why we're able to do this. So this t that's in this equation is functioning like this. This t is functioning as an integer of half a period. And again, why can we do that? Because of what we see here, okay? So it's not, we can't just randomly do this with anything. It's because of this periodic motion and because of the pattern that's set up here, we're able to do this, okay? So again, just to finish this up, so we see that not only when n equals 0 and n equals 1, but n equals 2, that's also a place where x equals 0. We see when n equals 3, time's going to be equal to this, but when you replace it in there, right, we can see again that x is going to be equal to 0, right, which would be at that point. And then again, when time is equal to, or when n is equal to 4, right, time is going to be equal to 2t, right, or a second, right, another full period, which we could see is going to be true, and that's what this is saying here. So again, when starting at the beginning, when is the value of x, and what is the value of x when time is equal to 0? We're just replacing time with 0, right? Here we replace time with 2t, but since we can see that of this periodic motion that time, or x is going to be equal to 0 every half of a period, time can function as some integer times half of a period. And so for anything afterwards, if you want to know, right, any other times when is x going to be equal to 0, you just put time. You can put 10 in there. N can equal 10, n can equal 14. But time is n equals 14. Do that math, and then that's what you're going to put in for t and replace in this equation, okay? Which is what I did right here for you when I was doing that math, all right? So again, hope this was helpful. Go back and watch it a few times. If it wasn't, ask your professor questions, ask your tutor questions, because they're going to really help you here, all right? I'm super proud of you, and I'll see you on the next video.